Okay, let's practice some problems. Elemental potassium and elemental bromine react to form one new chemical compound. Okay, so we're just going to focus on what reactants are there and what reaction type we're making. Okay, so for our reactants, we have elemental potassium as one thing. I'm going to make that down here. That's just K. Okay, potassium is not one of these 7 diatomic elements in Hofbrinkel. Okay, and Hofbrinkel is from chlorine, not potassium. So potassium is just going to be K on its own. That's just straight off the periodic table. Okay, now bromine, elemental bromine is in there, Hofbrinkel. So bromine is not just going to be Br, it's going to be Br2. Okay, so if I want these guys to react together, okay, to form one new chemical compound, I'm starting with 2 pure elements. I'm trying to make one single product. So, well, let's see. I'm going to make one thing over here. We're not going to really worry about what that product is for now, but I can tell what type of reaction this is going to be just based on what I have in the reactants. If I have just a single element and a single element coming together to make a single compound, I have 2 elements coming together to make a single compound, that is going to be a synthesis reaction. Oops. Synthesis reaction. A synthesis reaction has just elements coming together to make a single product, okay? Where they just smash together and stay together. Okay, let's look at another example. Water reacts and breaks down into the elements that make it up, okay? Well, in this case, this is really the only thing we have to go on. We just have water that apparently just breaks down and falls apart into a bunch of other stuff. So my only reactant here is water, which is H2O. Okay, it's reacting with nothing else. It just breaks down and makes something. So again, I'm not really going to worry about what I make on the other side here for now, but H2O is going to break down into elements. All right, so this is kind of like the opposite of a synthesis reaction. This is a decomposition. Decomposition. All right, so our water is decomposing or breaking down into the elements that make it up, the hydrogen and the oxygen. Okay, now the way that it breaks down into those separate elements is something we can deal with later. But for now, we can tell this is a decomposition reaction. So let's do a little exclamation point. Keep with the color coding. All right, let's look at another one. Dicarbon dihydride and elemental oxygen react to form 2 new chemical compounds. Okay, well, let's figure out what dicarbon dihydride is. Okay, so this would be, di is 2. Same here. All right, so dicarbon would be 2 C's, and then dihydride would be 2 H's. All right, this is reacting with elemental oxygen. Okay, so oxygen in the elemental form is just O, but we have to be careful. Is it one of those 7 diatomic elements? Okay, well, Hofbrinkel is oxygen in there, the of Hofbrinkel. So it is one of the 7 diatomics. So instead of just leaving it O, it's going to be technically O2. It'll pair up with itself to be a little more stable. Okay, so what I'm reacting in this reaction is C2 and H2, C2H2 as one compound, reacting with elemental oxygen. Okay, now this is something we have to be careful of. This kind of looks like a single replacement reaction. I have a compound reacting with some pure element. So this looks like the oxygen is going to kind of swoop in and take something's place and kick something else out as a pure element. But this because we're using C's and H's reacting with O2, it's more specifically going to be a combustion reaction. Okay, what it's going to end up making is carbon dioxide and water. Again, we don't have to really worry about that right now, but it's a more specific thing. It's and it doesn't really work like a single replacement where you get a pure element on the other side. Combustion reactions always, always, always make CO2 and H2O as their products. So just by telling that we have C's and H's reacting with O2, this is going to be a combustion reaction. Okay. Let's see, elemental potassium and lithium chloride react to form two new chemical compounds. So I have, in this case, an element, okay, that's being paired up with a compound of lithium and chlorine. Okay, so elemental potassium, just like before, is not a diatomic, so it's just going to be K right off the periodic table. Lithium is Li. Chlorine is Cl, and these guys should be together in a compound. Now, I have to be careful. I have to make sure this is a valid compound where all my charges cancel, okay? Otherwise, this wouldn't be in the reaction to react in the first place. So let's see. I'm going to double check the periodic table. Lithium has a charge of +1. It's in the first column. As an ion, it's got a +1 charge. Chlorine has a charge of -1 as an ion. It's in column 17. It's in the halogens group. So +1 and -1 are going to cancel out. I don't need any more Li's or Cl's to make this thing happy. It's just one of each. So that works fine the way it is. Okay, so if I were reacting these two things together, all right, I'm going to end up with one of these elements kicked out on its own, as the potassium is going to come and swoop in and take the place of something else. Okay, now how do I know that? Because we have a pure element reacting with a compound. Okay, that is a great sign of a single replacement reaction. Single replacement. Ooh, I'm going to run out of room. Oh, I can scooch it over a little bit. Yeah, I can fit my exclamation mark in there. Nice. Okay, so in this case, again, we're not really worried about what products we make, but just for the fact that we have an element and a compound reacting, that's not C's and H's, and it's not O2 reacting, it's going to be a single replacement reaction. Let's look at one last one here. Potassium iodide and lead 2 nitrate react to form two new chemical compounds. Okay, well, let's write out what we have. So potassium iodide is going to be, okay, well, potassium is K, iodine is I. All right. So what about lead nitrate? Well, lead, Roman numeral 2, means that we're going to have lead with a +2 charge. So lead is Pb. It's going to be a +2, just to write that there so I don't forget it. Okay, nitrate is a polyatomic ion. Ooh, it's good that I know those. Okay, nitrate is NO3, and the whole thing has a -1 charge. Okay, now since we're not really making the products here, it's not as huge of a deal if I have the right kind of formulas, but it is going to be important later, and it's good practice. So let's make sure I have the right formulas here. Well, my K has a positive charge in the first column. Iodine has a -1 charge as an ion, so positive and negative, those cancel out. So just having one K and one I in our formula is good to go. Okay, now what about these guys here? Lead has a +2 charge. My polyatomic ion nitrate, NO3, has a negative charge. So overall, this thing has a -1. This has a +2. It's not canceling out. I would need another nitrate. So to show that, I'm going to put the whole thing in parentheses. Say there's 2 of them right there. Okay, this is the formula of lead to nitrate. Pb, and my NO3 is there. The whole thing is there twice. Okay, so these are my two compounds I'm going to be reacting together. Now, even without the correct formulas, I can tell this is supposed to be a double replacement reaction. I have two compounds coming together, two typically ionic compounds coming together, and they're going to end up switching partners like a square dance. So, the K and the PB, the positive stuff is going to switch, or the I and the nitrate is going to switch, the negative stuff is going to switch. But in either case, I'm going to switch up the couples. Right? I'm going to end up with kind of two new pairings of these compounds, how these guys stick to each other and cancel that positive and negative charge. So the step I make on the other side here, I'll end up switching some guys around. So say I switch these guys here. So I end up with some new pairing here and some new pairing here. Okay. Either case, this is going to be a double replacement reaction because I have two compounds coming together to switch partners. Double replacement. Okay, so you can tell the type of reaction just by looking at what reactants are coming together. Okay. And if you're ever not sure, go and check your reference sheet, look at your reaction types, and that should help yourself out. Okay, from here, we'll be looking at how we can predict the products of a chemical reaction, actually figure out what we're going to make on the other side of the reaction. Here, or there.